we're back with mini lecture 4 out of 5 for the week. I think this is going to be the last time there are this many. Okay. So the tests we were working on earlier were to determine whether there are differences in one variable captured as either a mean or a proportion between two groups, right? So for example, we may have asked how often Democratic voters may support a given public policy measure versus other voters. And we did that through what are called difference of mean and difference between proportion tests. That's a t-test, right? You can read about that in the book, and you can check it out on Stata as well. Sometimes we may have more than two groups we want to compare between, right? Say Democrats, Independents, and Republicans. So we're not just looking at, is there a difference between this group and this group in terms of this other variable? We're looking at, is there a difference between two or more or three or more groups in this in this independent variable. I didn't go into depth on t-tests in the lectures because I don't think any of you are using them in your group projects, and because they are the simplest to understand and kind of get a grasp on your own. The book does a good job explaining them conceptually. There's plenty of resources on like the internet as well. I can provide some for you if you want. Instead, just type help t-test, help t-t-e-s-t, and it'll tell you how to do it. I think it's just t-test, dependent, independent, enter. But more often, and for more of you in this class, we're going to be looking at whether there is a difference between the average in this group, the average in this group, the average in this group. So you're looking for differences across more than two groups. In that situation, we use a test called ANOVA, which is an acronym for Analysis of Variance. We use this approach, here's the straightforward helpful thing, when we have a scaled dependent variable and a nominal independent variable with more than two categories. Scaled would be interval or ratio. So we've got an interval or ratio dependent variable and a nominal independent variable that has three or more than two categories. And we can start by creating a scatter plot. So here is feelings about Obama by political party, where feelings is a feeling thermometer. The party is coded so that 1 is Democrats, 2 is Independents, and 3 is Republicans. And what we see here is that each group has a different mean, but there are commonalities across the groups, right? There's no perfect, like all Democrats are 100s and all Independents are 50s and all Republicans are 0s. That's not how it is, right? It's spread more than that. And you see that here as well. Each group has a different mean, but there are commonalities among the groups. So Y bar sub D is your dependent variable, right? Feelings towards Obama, averaged, average is the bar, among all Democrats. That's the sub D. Right? Y is your dependent variable. The bar across the top of the Y, that line across the top that we call a bar, that means it's the average. And the sub D means it's the average among all Democrats. Similarly, Y bar sub I is average feelings towards Obama among Independents. And Y bar sub R is average Republican feelings towards Obama. We can also calculate an overall mean, so the average across all of our data, not taking into account what each person's political affiliation is. That's called the grand mean. It's just the mean across everybody. Our goal in statistical analysis is to explain the variation, and we can see that there is something different about partisan affiliation that leads people to like or dislike Obama. The purpose of ANOVA is really to decompose the variance in the dependent variable into two parts. A systematic component, which is the component explained by the independent variable, and the unsystematic component, which is the part that we can't explain with our independent variable. It's known as the error. If the error term is large, that means that of all of the moving around that our dependent variable does, only a little bit of it can be accounted for by the independent variable. In other words, if the error term is large, it means the independent variable does not explain much about the dependent variable. Right? So basically your dependent variable moves around a bunch. And we want to understand how much of that movement can be explained by our independent variable. Right? That's the relationship between x and y. That's the systematic component. What's left is the stuff we couldn't explain with our independent variable. That's the error. If there's a lot left in the error, it means the independent variable didn't do a very good job explaining all of the movement between x and y. It left a lot of stuff left over. For each observation and then for each group, we can calculate the deviation of the individual's score from their group mean, and we can calculate the deviation of each individual's score from the overall or grand mean. When we do that, we can differentiate between the individual's deviation from the overall mean, the deviation between each group, that's denoted with a J there, and the overall mean, that's the systematic component, and the deviation between each individual, I, and their group's mean. That's the unsystematic component. Does that make any sense? If it doesn't, shoot me your questions. Let me try to say it again, though. There are different, so like, we know what the overall average is, we know what the average for each group is, and then we know what each individual person's feeling thermometer score was. So we can find the difference between each individual and the overall average. We can find the difference between each group and the overall average. So for example, what is average feelings towards Obama, and what is the difference between everyone's average feelings and Republicans' average feelings in particular, right? That's the deviation between group and overall mean. And the distance between each individual's feeling and their group mean. So how far is this Republican's feeling about Obama from the average Republican feeling about Obama? That's the unsystematic component. That's the error stuff. In our example here, J equals 3, and that's because there are 3 groups. There's Republicans, Democrats, and independents, right? So there are 3 groups, so that parameter J is 3. We're going to add together all of the deviations from the grand mean, all of the distances between the overall average and each individual person, and then determine if the sum of those deviations is due primarily to systematic effects, so the effects of being a member of one group, or unsystematic effects, so the effects of randomness or error. And the way we do that is by squaring the deviations to remove negative signs. If we want to sum across, we want to say like, how far are these people from the mean? And is that distance due to the fact that they belong to a political party or some other thing I don't know, I'm not looking at right now? We don't care if somebody is really high above the mean or low above the mean. We just care how far they are. And so we're going to square the deviations. And what that does is remove any negative signs. So the first thing we do is sum the overall squared deviations from the grand mean. The second thing is sum the squared deviations of the group mean from the grand mean. That's the systematic component. And the third thing we do is sum the individual deviations from the group means. That's the unsystematic component, or the error. If the systematic part is large relative to the unsystematic part, then we say the independent variable, which is group membership, explains the dependent variable, which is feelings about Obama. Right? Usually in part. We rarely get something where everything about our dependent variable is explained by independent, right? Your feeling about Obama would have been or is affected by more than just your group membership. But if it's affected by your group membership, then the independent variable explains at least part of the dependent variable. And the converse is true as well, right? The dependent variable explains a little bit or tells us a little bit about your independent variable. All right, let's look at that again, and let's look at it a little deeper. If you're totally lost, go back and watch it again. If you're totally lost on that, come to me and I'll walk you through it again. This is really all about, like, we know these different statistics, right? We know what the overall average is, we know what the average within each group is, and we know what each individual's average is. And if we want to know how much of our independent variable explains our dependent variable, then we can look at how far away these things are from the overall average. All right. The ANOVA model, analysis of variance model, it lets us estimate how much variance in the dependent variable can be explained by the systematic group effect and how much of it is error. Right? It says that the score for a particular person in a particular group on the dependent variable, right, an individual person who belongs to a particular political party, their feeling about Obama, it's a function of the grand mean. It's a partially affected by everyone's average feeling. It's also a function of being in the J'th group, first, second, or third, Democratic, Republican, or Independent. And it's a function of the error associated with the ith individual, right? I just being the number, right? Just one random respondent, deviating from the ith group mean. So my score on my feelings about Obama is in part a reflection of society's average feeling. It's in part a reflection of the average feeling among my political party. And it's in part a function of other stuff that's not measured here. There are 3 types of sums of squares in ANOVA. So we took the squares to get rid of the averages. These are squares of the distance between the average and us. Sorry, we took squares to get rid of negatives. And now we're adding all of those squares. There are 3 different ways we can add the squares. The first is something called the total sum of squares, or TSS. That is the sum of the total squared deviations from the grand mean, right? Squared deviations is the distance from the average squared. The total sum of squares is just what's the average feeling thermometer, right? What's the average value in the whole population, or in the whole sample, sorry. What's the distance between this person's value and the average value? Square that. Then take the next person. What's the average value? What's the distance between this person's answer and the average value? Square that. Add the 2 together. That's your total sum of squares, right? Once you've done it for every person you've got or every observation you've got. The between sum of squares captures the component of the total variance that can be explained by individual group membership. And we get it by adding the squared distance between each group average or each group mean and the grand mean. So how different is the Democratic average or the average Democratic feeling to the average overall feeling? Right? We do that, and then we weight it by the number of observations in each group. So if we happen to have, for some reason, 100 Republicans and 30 Democrats responding to the survey, we can weight that so the unequal number of responses across groups doesn't skew or screw up or bias or mess up our results by just weighting by the number of observations in each group. So between sum of squares captures how much your political party membership can help us, or average political party membership can help us understand feelings towards Obama, for example. And then the within sum of squares, that's a measure of the error. Between sum of squares is how much does group membership, which is our independent variable, help us understand our dependent variable. Within sum of squares is a measure of error. It's a measure of how much other stuff that's not our independent variable explains. So it's the variance in the dependent variable not explained by being a member of one of these J groups. In this case, J is the political parties. So to do this, we calculate the difference between each individual's score and the group mean to which that individual belongs. So if I'm a political independent and my feeling score is 20 points lower than the average among political independents, then the distance is -20. We square it, which makes it 400. So that's my distance. And we're going to add those across everybody's. So your total sum of squares, well, let me go back. Okay, so your total sum of squares is all of the variation going on. Some of that variation is as a result of between group membership. It's the difference between average Republicans versus average Independents versus average Democrats. That's between sum of squares. The within sum of squares is the variance within each political group It's just unexplained. That's the unsystematic error component, right? So the total sum of squares is the between sum of squares plus the within sum of squares. All of the movement can be broken into movement within groups and movement between groups. In other words, your dependent variable y is a function of a systematic element, the sum of squares between, and an error component, the sum of squares within. What the ANOVA is now is a measure of how well the categories or groups of your independent variable explain the variance in your dependent variable. An ANOVA is a measure of how much of the variance is systematic, how much of it can be captured by you saying these groups matter. And now we have what we need to calculate a really important statistic in the ANOVA model, which is eta squared. Eta is a Greek letter that looks like a fancy lowercase n. It is the sum of squares between groups divided by the total sum of squares. So it is quite literally the proportion of variance in the dependent variable that is explained or captured in the independent variable. Now, this is all about hypothesis testing, right? We want to test and hopefully reject the null hypothesis that there's no difference between groups, that Democrats' average feelings about Obama and Republicans' average feelings about Obama and independents' average feelings about Obama are statistically indistinguishable from each other, that they're the same. We want to reject that null hypothesis, accept our hypothesis that political party membership helps explain feelings about the president, right? And we can do that with an ANOVA. In an ANOVA, we're computing a ratio for the systematic and unsystematic components. If the systematic part, that's the between variance, is large relative to the unsystematic or error part, then we can reject the null hypothesis of equal averages or equal means across groups. In practical applied terms, we have to adjust the sum of squares between and the sum of squares within by their degrees of freedom. Not super important to understand this at a deep level unless it's going to keep you up at night not knowing. But for now, note that the sum of squares between divided by j minus 1 is the ms, which is mean square between. Remember, j is our number of groups. And the sum of squares within divided by n minus j gets us our mean squares within. And n is your number of observations, right? It's the number of cases, the number of rows in your data. J is your number of groups, n is your number of cases. Degrees of freedom is what's in the denominator there. So once you've got your sum of squares between, you want your mean squares between, you divide the sum squares between by j minus 1. Once you've got your sum of squares within, you want your mean squares within, so you divide that sum of squares within by n minus j. And then you construct an f-test, which is a ratio between the mean squares between groups and the mean squares within groups. It is the ratio between the average explanation accounted for, or the average variance in your dependent variable accounted for by the groups of your independent variable, and the average variance in your dependent variable not accounted for by your independent variable. If you think well in terms of distributions, you should be aware that the F distribution is not symmetric, and that's because it's based on a ratio of two positive numbers. It's skewed to the right, and that's going to become important when we look for whether or not how to know the F statistic is statistically significant or not. It's worth knowing in general that when n and j increase, it becomes easier to reject the null hypothesis. More cases is better, more groups is better. And when we're using an ANOVA to conduct a hypothesis test, at the end of it all, what we're looking for is the statistical significance of the f-test. To find that, you use a handout. I posted it in Canvas just above the mini lecture. And I said you should, this is what you need to test this. You should have this with you. When you see the F statistic reported in one of these handouts, or anywhere, it's usually with two numbers in parentheses next to it. You already know what those numbers are. They're on the slide you're looking at now. So the degrees of freedom for the numerator is degrees of freedom for the between group. That's J minus 1. It's the actual number, the number of cases minus 1. So where the independent variable is Republican, Democrat, and independent group membership, where J is 3, the degrees of freedom is 3 minus 1, so it's 2. And the degrees of freedom for the denominator is the degrees of freedom for the within group, which is N minus J. So if I had 100 cases, 100 respondents giving me feelings about Obama across the 3 groups, then it would be 100 minus 3. So I'd have 97 degrees of freedom for the within group. You need those degrees of freedom numbers for the significance test. You need to know your N. You need to know how many groups there are so you can calculate these degrees of freedom. When you go to the handout that I posted, it'll talk you through how to use those degrees of freedom to find the critical value on that F test handout, and then help you figure out whether that critical value is statistically significant or not. If that test is significant, we can reject the null. We can say that we can infer from the sample to the population that there are differences in the means of the groups. If the F test is significant, we can say our hypothesis is supported by the data. Stata will do an ANOVA for you. It is just really important to know what it's giving you because it's going to spit out TSS and BSS and WSS, and you need to know total sum of squares and within and between. You need to know what the F statistic is. And at the end of it all, what you're doing is calculating your F statistic and then using the critical values on the handout I gave you and the instructions on the handout I gave you to find whether it is statistically significant or not. And once you understand how to do it kind of conceptually like that, then you can turn to Stata and let them do it for you. All right, so one more bivariate analysis, and that is correlation, and that will be the 5th and final mini lecture for the week. See you there.